Good afternoon, everyone. Thank you for attending this afternoon's webinar, Pile Testing, presented by Brian Barnes, Senior Engineer at Atlantic Testing Laboratories.
And good afternoon, everyone. So today I'll be discussing some of the test methods to evaluate driven and cast in place deep foundation systems, specifically piles. And what I'll be talking about today are the typical pile types we see in our area, the test methods for determining things such as pile capacity, integrity, and length, and what to expect from the test results. As with any type of testing, there are some limitations that we need to be aware of. So what are piles? Well, piles are a deep foundation system that are used to transmit structural loads to a deeper, more competent soil or rock strata. They're also used for bridge projects that cross water to provide scour protection to the bridge abutments. And the piles can consist of prefabricated piles such as steel, concrete, or timber, driven with a hammer. And typically in our area, we see the typical steel H piles, pipe piles, as well as timber piles as far as driven piles. There's also cast in place concrete piles, auger cast, or large diameter drilled piers. In any case, they'll typically develop their load carrying capacity through a combination of skin friction as well as end bearing. Typically piles installed with the tip into rock or a dense glacial till will have more of an end bearing component versus piles driven into a soft clay. So there's a few types of driven piles that we'll talk about. The photo on the left, that's an H pile, a steel H pile. The second photo in, that's a steel pipe pile. And sometimes the pipe piles are filled with concrete or water. Sometimes they're not filled at all, depending on the specification. But it's important to note that in both piles, you'll see markings on the piles. And I'll talk a lot about through the presentation about the blow counts. Blow counts are an important aspect of monitoring driven piles. There's some older pile contractors out there that will say a driven pile is a tested pile, because if the hammer hits the pile once and the pile drops 10 feet, it's probably not going to have as much capacity as a pile that's driven to 20 blows per inch with the hammer. The third photo over, that's a photo of a timber pile, which is basically, it's very similar to a wooden telephone pole, which is driven in the ground. And you can see on the top is kind of mushroomed out from being driven. And then the photo on the right, that's a sheet pile wall. And typically sheets are installed with a vibratory hammer, or sometimes a drop hammer, depending on the driving conditions. For the drilled pile types, typically the drilled piles are going to be they'll be installed using an auger to auger out a hole, and that hole will typically extend down to the bearing strata or the design depth. And once that hole is augered out, then concrete or grout is going to be placed in that hole to form up the pile or the pier. So the purpose of the pile testing is going to be to verify the pile capacities, and we always want to test to the ultimate capacity, which in allowable stress design is going to be the design capacity times a safety factor. For LRFD projects, the term nominal resistance or nominal capacity will typically be used, but we're always going to be testing to the ultimate or the nominal. We also want to determine the soil and rock characteristics. Even with soil borings, we don't know the exact soil pile interaction. There could be soil types where there's a loss of capacity over the time. which is relaxation. And there's also soil types where we'll gain pile capacity over time through soil setup or soil freeze. We also want to monitor the performance of the installation system. From a quality control standpoint, we want to make sure all the piles are installed in the same fashion using the same equipment across the site. We want to determine the required pile lengths for construction, especially for large projects with a lot of piles. If the piles go deeper than what they're planned on a large project, that could result in a large cost overrun. So it's sometimes important, especially on the very large projects, to do some pre-construction testing to determine what the actual pile lengths are going to end up. We also want to establish installation criteria, which is going to be how many blows per inch or blows per foot is required to achieve a specific capacity, as well as the depth to achieve that capacity. And that brings us to question number 1.
Okay, Brian, please continue.
Okay, question number 1, what capacity should driven piles be tested to? The answer is C, the ultimate capacity. So some of the methods that we have to determine pile capacity, prior to installation, there's a couple. There's dynamic formulas and wave equations. I'll go into these in a little bit more detail, but dynamic formulas, per the Federal Highway Allowable Stress Design, the safety factor using dynamic formulas is 3.5, whereas with wave equations, it's 2.75. So the dynamic formulas are not a very good method for evaluating pile capacity prior to installation. During installation, there's dynamic pile testing, which there is an ASTM test procedure. It's D4945, and the piles are tested as they're being driven into the ground. After installation, static load test can be performed, which again, there's an ASTM test method for the static load test, as well as dynamic testing through a restrike. The one thing with dynamic testing is there always needs to be some sort of weight or some sort of hammer to strike the top of the pile to create a dynamic force to test the pile. So the dynamic formulas, that's basically a mathematical solution based on the hammer properties. And from that, an inspector in the field can estimate the penetration resistance required for a pile capacity. And it's typically not recommended because you really don't know exactly what the hammer energy is unless you're actually testing it. So there are some charts out there. Here's an example of a pile bearing chart, which is specific to the ICE 42S diesel hammer. And you can see this is based on the engineering news formula. Right here's the formula, which is based on the hammer energy as well as the pile set, or how many blows per inch the pile is being installed to. So in the field, if the inspector was observing the hammer operating at 47 blows per minute, which is a stroke of 6.5 feet, which that can be visually observed in the field with a diesel hammer. And if the inspector was observing a pile set of 4 blows an inch, that pile would have a capacity, an estimated capacity of 75 tons. One of the things I want to point out with this chart is down on the bottom. It says driving at 10 blows an inch is considered practical refusal. And it goes on to say driving in excess of 10 blows per inch or more for 6 inches or 20 blows an inch is considered improper use and will void the hammer warranty. So typically see a few specs out there that require piles to be driven to 20 blows an inch, but contractors don't like that because some of the hammer manufacturers won't warranty the hammer. The wave equation, that's another method to estimate pile capacity before driving. And this is basically software that can simulate the driving system based on actual soil conditions from soil boring logs, the pile type, as well as the hammer that the contractor is going to use prior to driving. And this is going to give the inspector a bearing graph that can be used in the field. This also estimates what the driving stresses are going to be on the pile. And we typically want to keep the driving stresses for steel below 90% of the yield strength of the steel material. The wave equation, it doesn't determine how deep a pile is going to be driven to achieve a capacity. That needs to be tested in the field. But what that does, it determines the blow count versus capacity, as well as the stresses for the hammer and pile setup. So here's the typical input for a wave equation analysis. Over here, the hammer information is inputted. The cushion information for the specific hammer that the contractor is using. The pile information, the pile size, pile length. And over here on the right is going to be where the soil parameters are inputted based on soil boring logs. One of the things that has to be done in this analysis is we have to estimate the percentage of shaft friction versus end bearing for this analysis. And here's one of the printouts. This is specific to the ICE I-19 diesel hammer, which has all the information, and then the soil distribution along that pile. And then here's a bearing graph. So if in the field, the inspector is going to be looking for a capacity of 350 kips for this setup, the inspector is going to be looking for a blow count of about 60 blows per foot, which is about 5 blows per inch at a hammer stroke of about 8.3 feet. And from that, we can see that the stresses are going to be, if typical steel is 50 KSI steel, so 90% of that's going to be 45. So the stresses are well below that. The other thing I want to point out is if the required capacity was going to be 600 kips, we'd see from this setup that it would take about 240 blows per foot to achieve that. So this probably wouldn't be a very efficient setup if 600 kips was required for the project. And that brings us to question 2.
Okay, please continue, Brian.
Okay, question 2. WEEP analysis estimates how deep a pile would be driven to achieve a specified capacity. The answer there is false. It's going to estimate a blow count to achieve a specified capacity, as well as the stresses. So to get into static load testing, in the static load test, a load is applied to the top of a pile through a series of weights or a jack system. And the test is conducted to failure the pile or 200 to 300% of the design load, which is a safety factor of 2 to 3. And during the test, the vertical displacement at the top of the pile is measured. And here's the typical setup shown in the ASTM. The upper setup shows reaction piles with the reaction beam with the jack over the top of the pile. And the second setup is just a weighted platform to create resistance for the jack to put a load into the top of the pile. And here's an actual setup. So you can see from this setup, there had to be 4 reaction piles installed for this project just to test this one pile. So you can see there's quite a lot that goes into that. And typically the contractors are required to set this up, and the inspectors or engineers will be out there to monitor the test and record the test results. Here's another setup using the weighted platform method. So you can see all the weights that are necessary to test this single pile. And here's some data from the Federal Highway of a typical static load test. So some of the things to point out on here, this elastic deformation line, that's the elastic shortening line for the pile material. And this is the actual load curve. So each point represents a load versus deflection at the top of the pile. And you see this has a failure criteria line drawn on it. Every project is going to have different failure criteria, really dependent on the engineer's preference. So in this case here, you can see that based on this data, the ultimate pile capacity is going to be around 475 kips based on the failure criteria for this test. Here's another actual test. This was a 90-foot long H pile, which was driven into a clay soil, and the test was done several days after the installation. And this test is a it's a static load test, but it's a cyclic DOT cyclic load test, where the pile was loaded in 3 cycles. So the first cycle, the pile was loaded to the design load, which was 60 tons. Then it was unloaded, and it was loaded again to twice the design load, or 120 tons, unloaded, and then loaded again to twice the design load. And at this point, the load was held there for 24 hours. So this test took about a day to run to here, and then it sat there for 24 hours. And based on the test, it's got a permanent set of about 1/4 of an inch. This is another test on the same project, a 90-foot H pile. And this is the DOT quick load test. So basically, the pile was loaded up to twice the design load. And then it was unloaded and shows a permanent set, again, of about 1/4 of an inch. In this test here, this took about 8 hours to perform. And you'll see the elastic shortening line here. This is for a free pile with no skin friction on it. But because this is a pile that was installed into clay with a lot of skin friction, the actual load curve doesn't match the elastic shortening line. So some of the advantages in the test, the test is performed using loads similar to the service loading. It's a static test. This test has been around for quite a long time, and because of that, it's typically considered the most accurate for evaluating pile capacity. And Federal Highway recommends a safety factor of 2.0 for static load test data. Some of the disadvantages, there's extensive setup, which is time consuming, can become expensive, and it only indicates the load carrying capacity of the pile. Nowadays there is instrumentation that can be affixed to the pile to determine what the forces as well as deflections are throughout the length of a pile in a static load test. So to get into dynamic testing, dynamic testing has been around since the 1960s, and that involves taking measurements at the top of the pile, during which a drop weight or a hammer is dropped on top of the pile. Typically that weight needs to be about 1 to 3% of the capacity that's trying to be achieved. So it was originally developed to evaluate pile capacity, but over time the technology has evolved and now provides information about the driving system as far as stresses and hammer energy. And besides driven piles, it can also be performed on auger cast and drilled shafts after they're installed. And it's considered more accurate than the energy formula evaluation methods. So some of the equipment, strain transducers and accelerometers are affixed to the top of the pile, which measure the force and velocity. And those measurements are analyzed by the pile driving analyzer, which is what you see here. And here's a photo of the gauges. So these long, slender gauges, those are the strain gauges, which measure the force in the pile. And the smaller gauges on each side are the accelerometers, which measure the velocity. And these are typically going to be installed 1 to 3 pile diameters below the top of the pile. So it's important during the pile test to make sure the test piles are a little bit longer than the production piles to allow for dynamic testing. So this is an H pile. So typically with the H pile, we would just drill holes through, and then we would bolt the sensors on. If it was a round pipe pile, we'd have to drill it and then tap it to be able to screw the sensors to it. And then for wood piles, we would typically use wood lag screws to attach the sensors. But in any case, we're always using 2 sets of gauges, one on each side of the pile, 1 set on each side, so that we can account for any bending or non-uniform impacts at the top of the pile. And just some of the photos of the setup that goes into it. And you can see attaching the sensors, and then we have the cables. Nowadays, the equipment is wireless. We can still wire as well, but we have Bluetooth capabilities, so we don't need these wires. And then everything is pulled up into the leads, and the pile's tested from there. So as I mentioned, the gauges are attached to the top of the pile, and as the pile is being driven into the ground, the data is being analyzed by the pile driving analyzer, and during data collection needs to be interpreted by the engineer. So one of the things we look for is the results should match up with soil boring data for the site. to make sure that we have good data. A little bit of theory. When the hammer impacts the top of the pile, that generates a compressive wave, which the compressive wave travels down the length of the pile. And in easy driving conditions, the tip of the pile will actually stretch and advance into the soil. And when that happens, that'll generate a tensile wave that goes back up the pile, which will be measured by the gauges. In hard driving conditions, driving to rock or hard glacial till, the compressive force goes down the pile. However, when it gets to the tip can't move. So that generates a compressive wave, which goes back up the pile. And when that happens, that doubles the force at the toe. Driving into rock, driving into hard glacial till, it's always important to monitor the stresses at the toe of the pile. So during the testing, dynamic testing measures the pile capacity at the time of testing. Doesn't account for any long-term changes, which might happen due to relaxation or setup. It also monitors the driving stresses at the time of testing. And as I mentioned, we typically want to keep the steel stresses below 90% of the yield strength of the material. With concrete piles, the tensile stresses are more important to monitor because the concrete is weaker in tension, but we typically don't get into a lot of concrete driven piles up in our area. We're also measuring or monitoring pile integrity, if there's any damage or potential damage going on, and the program will indicate the location as well as any general severity of damage as the pile is being driven. Also monitoring hammer energy and how well that hammer is operating compared to the rated energy for the hammer. And in any event, we need to make sure we have good data. If we don't have good data, then all the other results are going to be meaningless. So some of the common data errors we see, we could have loose sensors. We always check our sensors before we pull everything up into the leads to make sure everything's tight and working. But especially for piles that take a long time to dry, sometimes the bolts will loosen up, which we can see from the data, and we can make that adjustment as the pile is being driven. There could be changes in the pile properties. Sometimes with spiral welded pipe piles, if we get our sensors too close to that thicker weld, that's going to alter some of our data that we need to be aware of. We could have background vibrations from the hammer as well as the leads. Or we could have bad cables or sensors. We always like to attach everything on the ground. The contractor's gotta be able to pull the pile up into their leads, and sometimes the gauges or cables can get damaged. So they're expensive, so we try to do what we can to make sure we prevent damage, but sometimes it does happen. So once we collect our field data and we're satisfied that the data is good, the next thing we need to do is run a CAPWAP analysis, which stands for Case Pile Wave Analysis Program. And this is basically a signal matching process of our field data to determine the soil properties, the resistance distribution, and stress distribution along the pile. It's an iterative process, and once we get an acceptable match quality in the program, we know we've achieved our result. And this provides us a better estimate of the pile capacity. In the field, we typically come up with a range of capacities, and it's typically going to be an overall capacity. We don't have a real good handle on the skin friction and end bearing component until after we do the CAPWAP analysis. So it's typically recommended that 20 to 40% of the piles that are tested have a CAPWAP analysis performed on them. So some of the advantages of dynamic testing: provides more information about pile integrity, the stresses in the pile, as well as any potential problems with the driving system. And typically we can test anywhere from 10 to 15 piles per day. We're really limited by how fast a contractor can get around the site with the hammer or the drop weight. Some of the limitations, since we're testing, at that specific time, we can't account for soil setup in cohesive soils, which is sometimes a gain in capacity. Opposite that is relaxation or a loss of capacity, which can sometimes happen in dense, non-cohesive silts and sands below the water table, as well as some shales. So in cases where these soils are prevalent, it's always recommended to do restrikes just to monitor what the long-term capacity is going to be. For piles, particularly long piles through compressible layers, we don't evaluate the down drag or negative shaft resistance. That's something that needs to be evaluated by the designer. One of the things that's important is the results are generally conservative at high blow counts. So we typically like to be in the range of 4 to 8 blows per inch when we're doing the testing. Once the pile gets to higher driving resistances, typically 10 blows an inch, the dynamic tests are typically going to be conservative. And then lastly, we're only testing a single pile. So if there's any group effects for a pile cap, that's something that needs to be also evaluated by the designer. And that brings us to question number 3.
Okay, please continue, Brian.
Okay, question number 3. At high penetration resistances, which are blow counts greater than 10 blows an inch, dynamic tests are generally conservative. Answer is A, true. So as I mentioned, a restrike should always be performed to evaluate the long-term capacity, where you have soft cohesive soils or shales which exhibit relaxation. The restrike should always be performed with a warm hammer, particularly for the soil setup cases, because if the hammer doesn't fire right off the bat, the soil setup could be broken free, and to get a good setup test, the contractor might have to wait another period to be able to come back and test it. And typically restrikes can be performed anywhere from a few hours to several days, depending on the soil type. So for the clays and the shales, typically 5 to 7 days is what we see in specs. For other soils, typically 24 to 48 hours is a typical time period. So just to run through some examples quick, this was an H pile that was driven into a dense layer. And I say a dense layer because the soil borings didn't go deep enough, so the pile was actually penetrating into some soils that we didn't have any data on. So you can see here, here's the force and velocity record at the top of the pile, where the impact happens. And then here's the force and velocity at the pile toe. And you can see from this data, the force is high. The velocity is pretty much 0, so that's an indication that the pile tip isn't moving into the soil. And then down here, these R values, RX7, are different capacities for different soil damping factors. And this is going to tell us what we have for an estimated capacity in the field. So that's where we come up with the, I mentioned earlier, we typically come up with a range of what the capacity may be depending on the soil conditions. Here's an example of an initial drive. This was an H pile driven into a soft clay. And the designer for this project, they performed cone penetration tests. And they designed the pile to account for some setup in their capacity estimates. So looking at the data, at the top, it impact, down at the bottom at the toe. We can see at the toe, the velocity is high, force is low. So that's an indication the pile is moving through the soil pretty fast. The other thing we look at down here is the wave up. So the slope of the wave up line is going to be an indication of how much skin friction is on the pile. And in this case here, it's relatively flat, so there's not a lot of skin friction. And if we go down to the RX7, RX9 capacity values, they're around 295 to 305 kilonewtons on initial drive. So 5 days later, a restrike was performed on the same exact pile. And you can see from the data, the velocity actually goes negative before it reaches the toe. And if you look at the wave up line, it's got a pretty good slope to it now. So that's an indication it's got some skin friction on it. And then if you look down at the RX7, RX9 values, they went from around 300 kilonewtons to up around 849 to a little over 1,000. Here's an example of some apparent damage. And you can see from the force and velocity record at the toe, the velocity's high, force is low, so that's an indication the pile is moving through the soil. But you can also see a similar change in force and velocity about halfway down the pile. And if we look at the wave up, it looks like a toe reflection. And there's a line here which is called that's the beta line and the beta value, which I'll talk about next. But that indicates that there's damage in the pile, and it also indicates the location or potential location of the damage, about 17.2 meters below the top. So in this particular case here, these were I believe these were 50-foot H piles that were spliced together with a splice plate. And it is believed that the weld wasn't very good where the splice plate was to indicate this damage. And here's the beta values I was talking about. So 100%, if the beta value is 100%, it's a uniform pile. Slight damage is 80 to 90, damage is 60 to 80, and less than 60 is broken. And so if there is potential damage in the pile, that needs to be evaluated by the designer to determine what should be done next for the project. Here's an example of an H pile driven to rock, and we can see from the data down at the toe, high force, velocities 0, so the pile is not moving. And we have a large reflection at the toe, which indicates a lot of end bearing. One of the things I wanted to point out, the CSB, that's the compressive stresses at the bottom, and the CSX is the compressive stresses at the top. And so in this example, you can see the stresses at the bottom are actually higher than the stresses are at the top of the pile because of the increase in force being driven into rock. And here's a photo of a damaged H pile. This came from the Ohio Department of Transportation. They did some test studies on driving H piles to rock at 20 blows an inch. And one of the things I want to point out is in the dynamic testing, I showed earlier the compressive stresses at the bottom. Well, since we don't have gauges at the bottom, what we're actually measuring is the average force at the bottom for the entire cross section of the pile. So if you have a sloping rock condition where one side of the pile hits the rock before the other, you can have a stress concentration there, which could cause some pile damage. So just because the stresses are low doesn't mean that the pile isn't being damaged. So again, that's another thing that needs to be evaluated by the engineer and based on the soil or rock data for the site. So the contractor's role, they need to provide safe access to and around the work area so we can get up close to the piles to do the testing. There are instances where we get on site, the pile is already up in the air. So we require that they have personnel drill the pile and attach our gauges to it. We also need the project specifications, the hammer specifications, as well as the pile properties that the contractor's using on the project. That brings us to question 4.
And we do have a couple of questions if you want to answer those while we're waiting. Is there a difference in testing requirements if you have friction piles versus end bearing piles?
No, not that I've seen. I mean, dynamic will give the capacities for either case. But usually with friction piles, you typically want to do some sort of setup test for a friction pile.
All right, you can continue with the presentation, please.
All right, question number 4. Race strikes are performed during dynamic testing to evaluate the long-term pile capacity. That is true. So now I'm going to talk a little bit about some other tests that are typically performed on auger cast piles and concrete drilled piers. The first one is a pile integrity tester or pit testing. With this test, this can indicate potential defects in concrete piles, shafts, concrete filled pipe piles. It can also be used to determine unknown pile lengths, and as well as some pile information for existing structures. So this is considered a low strain test, whereas dynamic is considered a high strain test, where with the high strain it's got a very large, we're putting a large impact force to the top of the pile. In this low strain test, we are taking an accelerometer, which is affixed to the top of the pile, and then striking the pile with this calibrated hammer, which will generate a compression wave, which will travel down the pile and then come back to the top. So if we know the pile material, we know the wave speed. From that, we can determine, what the length of that pile is. So this is a quick and easy test, inexpensive. You can typically do 20 to 30 piles in a day. There are some disadvantages. Sometimes with auger cast piles, they're not a uniform section down through, which can produce secondary waves, which can mess up the data. And the test is most reliable for lengths less than 30 times the diameter of the pile. So just to go through some examples, here's the impact force at the top. It's nice and smooth through the length of the pile. And then here's the reflection where we would expect to see the toe based on the wave speed of the material. So this is an example of what good data looks like. Second one down, again, here's the impact force. Things are smooth. And then there's not a lot at the toe where we'd expect to see the toe. And that's because if you look here, the length to diameter ratio is 49. So it's this pile is typically longer than what is typically ideal for the test. Here's one where there's something going on at the top. There's a lot of secondary stuff going on, so there's probably an issue at the top of the pile. Here's another one, impact force. Things are relatively smooth, but we see a reflection much sooner than where we would expect to see the toe based on the wave speed of the material. So either this pile is really shorter than we would expect, or there's some sort of change in the area of the pile at that location. Cross-hole sonic logging. This is a test that's typically performed on larger diameter drilled piers, caissons. And this determines the concrete quality between pre-installed steel or PVC tubes using high frequency signals between a transmitter and a receiver installed in opposite tubes. So you can see here, here's the tubes that are installed. These things are typically installed around the rebar cages, and then they're lowered down into the shaft, and then everything is concreted. So to perform the test, transmitter is lowered down one side, receiver lowered down the other, and then there's high frequency signal that is passed across and picked up by the receiver. And here's a some data. So you can see the arrival times. This is a waterfall diagram, which is very helpful. So you like to see consistency in this. So this is an indication that the concrete quality between the transmitter and receiver is uniform throughout the length of the shaft. Here's another example, some data. And you can see in this example here, you get down to about 30 feet and there's some sort of anomaly there. The data isn't consistent. So that's an indication something's going on there. And in cases like that, sometimes the engineer will require to take a core of the shaft to try to find out what's going on down at that 30-foot depth. So there is some setup that goes along with this. One thing I forgot to mention is these tubes to test. They need to be filled with water or antifreeze to conduct the test. So some of the advantages, it's able to identify any issues with the concrete in between the tubes. It's widely accepted. I have seen it specified on a few jobs up in New York State for DOT projects. Some of the disadvantages, if there isn't good consolidation around the tubes, there could be air pockets, which will present issues with the data. Same thing with large reinforcement. Sometimes that can skew the data. And it's not able to address any of the concrete that's outside of the rebar cage, just everything that's in between the two tubes. The thermal integrity profile. This is a relatively new test method. We did just see it in a spec somewhere here. I can't remember if it was in New York State or not, but basically uses heat generated from the curing process to assess the quality of drilled shafts. And here's the equipment. And these thermocouples are attached to the rebar cage along the length of it. And that's all cast into the drilled pier. And as the concrete cures, the temperatures are recorded. and basically looking to see if there's any drastic changes in the temperatures throughout the length of the shaft. So this can identify any inclusions, bulges, variations in cover or cage alignment, and results are typically available in 48 hours or after the curing process. Some of the disadvantages: it is a relatively new method, and there are some boundary conditions that can affect results. One of the ones is groundwater. So it's important to have to know where groundwater is at the site, so that when you're looking at the data, you can determine if the changes in the thermal data is due to a high groundwater table. And that brings us to question number 5.
Brian, another question. Pile testing is performed for design or construction assurance?
Well, it's performed during construction, but it's to verify the design capacities.
Okay, please continue.
Question 5, what test method is used to determine the concrete quality of drilled shafts? That's D, all of the above. Then the last testing I'll talk about here is the LITE length inductive testing equipment, which can be used to evaluate steel piles, which uses a voltmeter, which detects any changes in metal. So typically it calls for this for sheet pile walls if somebody wants to determine how deep an existing sheet pile wall was. One of the problems with it, or one of the issues with their limitations, is you can see here you have to get real close to the wall to install a PVC casing. So you have to hire a drilling subcontractor to do that. The other thing, the engineer is going to have to determine how deep to install that casing relative to the wall. So basically what that does is that voltmeter, lower that down inside the casing, and that determines where the metal is, and with that you can determine the bottom depth of the wall. So that concludes my presentation, and I'll open things up to any questions.
Do not appear to be any further questions today, Brian.
Okay. Well, my email address is up there on the screen, so if anybody does have any questions, feel free to reach out. And I think everybody's time for today.
Thank you, everyone. That concludes our presentation for this afternoon. Please remember the PDH certificates will be sent to your email address that you registered with over the course of the next several days. Thank you and have a good afternoon.